Hello and welcome, everyone. Thank you for joining me today. My name is Malay and I'm an offering manager at NI. For this section of the webinar, we'll be talking about some of the interesting areas of research in millimeter wave and how we can use the USRP software-defined radio platform. I wanted to start off by talking about some of the trends that we are seeing and what's driving them. So wireless technology is very broad, but cellular has kind of become the key driver for many of the pieces that we, from commercial reasons drive today. And when we talk about cellular technology, spectrum becomes kind of the first thing that we talk about. When we are looking at new technology, new spectrum definitely becomes key. Millimeter wave got introduced in 5G. I'd say it's not probably deployed, but people are finding it interesting. And then people are expanding to different frequencies, right? So we have millimeter wave and then also FR3 frequencies, which are more midband, and then also sub-terahertz, which are at hundreds of gigahertz. So these all become really interesting aspects and are kind of related. Then kind of moving from the spectrum to some fundamental applications that start to drive this technology and make it interesting. Satellites or non-terrestrial networks, these are both kind of really prevalent, and kind of driver for many of the millimeter wave feasibility studies. And then also sensing and communication, autonomous vehicles, cars and trucks and others, they all need to sense, right? And they all need to communicate all the time. And there are a lot of advantages of even kind of sensing your environment while you're trying to communicate, right? So these all become fundamental in we're trying to do with this new technology. And then kind of the last piece, and which is why new spectrum gets explored in the first place, is as our kind of requirements increase, more number of users, higher data rates, optimization becomes key, right? And we've got kind of really studied very well when we started to do 5G and evolving further as we look at beyond 5G in all other communication spaces as well. And one of the most obvious, but we can't go about without mentioning, technology trends that is driving, especially the optimization, but many of these other pieces also, is AI and ML, right? How can we use that to move some of these areas forward or to do them better than we are doing today in traditional signal processing? So this is kind of a whole new area that adds another dimension to a lot of the research that we're doing. As we kind of talked about earlier, cellular seems to be, from a commercial sense, a lot of kind of the key driver for new research areas to be looked at. And so it makes sense to look at timeline on which cellular technology works. This is a fairly popular way to look at it. EG is approximately 10 years. And then maybe, you spend the first 4 or 5 years evaluating, exploring all the different possibilities. What are some of the key applications that we envision that's going to drive these requirements in the future? And then maybe the following 5 years in working on which one of these will go into the standardization. And right now, somewhere in the cusp, right? And I'd say this is probably the peak period where we want to kind of start trying to understand the answers of the research that we're doing. Right, and hopefully start converging to some of the key things that we want to put into the 6G standard. As we saw earlier, there are many different kinds of technologies and many different areas that we could focus. Why millimeter wave? And I'd say one of the main reasons why we started thinking about millimeter waves was the most obvious, right? Because of the availability of spectrum, where for the sub 6 gigahertz, it's very kind of densely utilized and kind of squeezed out almost all that we can for the sub 6 gigahertz. And as the data rates and requirements increase, we want to find out where we can get that. And moving up the frequency chain is one of the kind of first things that we would look at. And we did that for 5G. We haven't fully solved it yet. There's still many open challenges, especially kind of in terms of kind of the mobility use case. But nevertheless, we see some pickup. Some of the new things perhaps we didn't really consider when we started talking about millimeter waves and was kind of this prevalence or importance of sensing in communication, right? Being able to sense the environment that you communicate helps you communicate better. And then also applications that require both. An autonomous vehicle kind of comes to mind, but there are many such as AR, gestures, things like that. So all of these sensing applications, they work better at higher bandwidths, which are available at millimeter wave. And so we have now a bunch of these areas that could benefit with us better understanding how millimeter wave can work. And that's kind of the motivation on why we're doing this webinar today and why we would like to see some research in this area. We briefly talked about the different bands, and I thought let's kind of take a look at what are some of the bands under consideration today. The FR1 or sub 6 gigahertz band, this is the most well understood and the most well deployed. And even in this, we're seeing some new kind of ways that we can continue to utilize them. And, it's still going to be kind of majority of the deployment that's going to happen. But if you look a little bit beyond, we started looking at FR2, which is about 22 to 26, 28 gigahertz. And then, of course, 40 and so on in the 5G days. And then now FR3, which is kind of the mid band, between 10 and 20, 22 gigahertz. This is also becoming an interesting band for us to look at because it's utilized in some kind of geographic areas, but which also means that for a lot of the places, the band is still empty, right? And so maybe that could be a little bit easier to use somewhere between what we're doing, how well we understand sub-6 versus the challenges in deploying millimeter wave in terms of range and mobility and things like that, and cost also. And then as we look at some cutting edge applications that may drive next level technology like XR, AR, VR, then sub terahertz, which has even more bandwidth available. And so not only can kind of transmit copious amounts of data, but also can increase the sensing accuracy in kind of the short distance that it can reach immediately, right? So all of these kind of become different use cases that may drive millimeter wave from the generic communication to more maybe specific application-based use cases. And that's what kind of is keeping us interested in the space. So now coming to some of the interesting parts as well, how do we kind of look at, how do we research these areas? What are some of the tools available? And, from NI, we have, I'd say, broadly two platforms that could be used to set up millimeter wave systems, understand them better, and look at different research, kind of study different areas. We have the USRP platform. I think most of you would be very familiar with this. This is kind of our go-to platform, and it has a long range of products in it, but it kind of optimized for size and weight and cost, can do multiple channels typically, but also maintains the software-defined radio architecture and has a very, very extensive kind of library and community built around it, right? Making it kind of providing you some really good starting points for maybe the different applications that you're targeting. And then we also have slightly larger, but, higher performance, maybe instrument grade systems, have kind of additional perks like they're all calibrated. They typically can handle larger bandwidths and larger data, and then have some very, very good kind of data aggregation and synchronization architectures all built into the platform, right? And so if you're putting together kind of more of a system level setup and, you're really trying to push the limits of where millimeter wave or sub terahertz can go, then this could be also a good platform to consider. So each have their own strengths, and, we'll kind of go into how we can use them and for what kind of applications that we can target. So with that, let me start with the USRP X410 because, in some sense, I feel like this is the default USRP to be considered if you are looking to kind of start dabbling into setting up millimeter wave systems. It has kind of the extended bandwidth, with 400 megahertz, and the inbuilt frequency range is up to 7.2 gigahertz. And this is where, we can pair with the TMYTEK up and down converters and the BBox beamformers to kind of translate the RF to millimeter wave frequencies, right? And then you can use that to set up a full end-to-end millimeter wave system. And it's based on the Xilinx RF SOC architecture. So you have a lot of the kind of signal processing capability that that comes with the FPGA. And then we have LabView and UHD and GNU Radio to help you program, right? So it works with MATLAB, it works with GNU Radio, it works with LabView, almost any software, OAI, open air interface, right? And so, we'll see some of that later on, but it's a really versatile USRP platform, much in the mold of kind of where USRPs have been strong, but, we've now increased like a lot of the RF and signal processing capability with this. We also have another product based on RF SOC architecture, Xilinx RF SOC architecture. And this is our kind of latest USRP. It's the X440. It exposes all 8 channels that are available on the Xilinx RF SOC and provides for much higher bandwidth. This can do about 1.6 gigahertz per channel. And it's IF only, right? So it does IF or baseband only. So you definitely need a front end to put in front of it to reach mmWave, right? Or any other frequency. But the additional bandwidth could be valuable, right? When you are looking at higher frequencies and maybe you want to test kind of your waveforms or other things at these very high bandwidths that it supports. And then again, from a programming perspective, this one focuses more on open source capability. So, we have the UHD drivers and GNU radio, and you can stream a lot of the IQ data directly into powerful PCs for some post-processing or do some of the signal processing on board on the Xilinx SOX RF FPGA. One other thing, the X440 also supports phase coherence, right? And so that's very unique and I think could be valuable for many applications, especially as you increase bandwidths, becomes harder to keep things stable and phase coherent, but this USRP supports that. So this could kind of look at applications that both use kind of communication technology and MIMO, but also maybe radar and things like that. Right? So it's a little bit more versatile, but also it needs a front end in front of it. Now that you have these USRPs, how do you set up a system mmWave research, right? And so maybe just starting off by kind of exploring some of the areas that we've seen are popular for research in this area. So channel measurements, that's always key. Channel is important for any communication system. And honestly, probably FR2 channels are not as well understood as sub-6, right? For which we have very strong signal processing efficiency and capability, maybe a little bit less understanding for FR2. Then communication and sensing, both to sense the kind of objects and things like that, but also to sense the environment, right? So you can maybe adjust your communication to perform better in different environments, right? And then some new areas coming up, kind of fundamental new materials, technologies, reconfigurable intelligent surfaces. These help direct the radio waves, corners and things like that. And for mmWave, this becomes really important, right? Because you typically need line of sight and you need to be able to direct the beam, right? As opposed to sub-6, which is more kind of omnidirectional. And so these kind of technologies could be really good at aiding the adoption of mmWave. Beamforming, beam management, beam steering. These are just fundamental technologies needed for communication, all stem from the fact that, as you grow higher in frequency, your range decreases, right? And so you need to form beams and you need to manage and to find the device. And if you're really looking at mobility use case, you need to be able to track them. So these all come fundamental. And then MIMO, we talked about it earlier. Again, it's almost impossible to do mmWave without MIMO. So it's kind of even say a core piece of technology. Kind of set up prototype and research some of these applications. What does a typical system look like, right? So this could be one option. So we have the TMYTEK beamformers and the up and down converter as kind of the front end that operates in the mmWave frequency ranges, it up converts. Then we have the USRP, which is the radio and the workhorse. It does signal processing. It does kind of the RF piece. And then we have the PXI chassis, which is great for some of the controlling at the system level, aggregating all the data, storing it. Maybe you want to post-process it in MATLAB. So this kind of helps you do all that. And then we can also add things like FPGA coprocessor cards that could do some of this processing real time inline. And that could really accelerate post-processing and then things like channel sounding and stuff. It helps you kind of do the channel sounding and channel measurements much faster, right? If you're able to do some of the processing inline on the FPGA. And then we have some software kind of that glues the whole system together, making it easy to use. So all the controls, the frequencies, and sometimes, as you're doing higher bandwidths, there's actually quite a bit of optimization needed so that, you kind of maintain the integrity of the data flow. And so we've taken care of a lot of that in this kind of glue software that we've built. Takes all these different pieces and makes them kind of all work together as one system. So this kind of becomes a really handy system to essentially probably record and transmit mmWave and record the environment. So this could be kind of a fundamental piece for a lot of the research that you would be trying to do. And then there's like another category of research where you require an end-to-end system. Like that means that you kind of not only need the physical layer and the waveform, but you're looking at more from a system level. So you maybe, you need to measure things like throughput, or sometimes it's just good to have a demonstration that is kind of more closer to real life. And for that, we have this mmWave system that uses the OAI or open air interface 5G software stack. And here I have to call out and thank our partner, All Be Smart, who've done kind of a lot of the work of integrating and putting this stuff together. And they work closely with TMI Tech and with us to do this. And now I'd say, we have probably one of the world's only open standard compliant 5G FR2 system. And you'll see this in the demo later today and, perhaps got talked about a little earlier as well. We're really proud of this, and I think it's going to be kind of a really great starting point for a lot of end-to-end 5G research. And the base station side, we have this OAI box, which is a server that has all the right software stacks and drivers in the software, and a really neat dashboard kind of where you can see everything. And then we have the USRP that acts as a radio, and then the TMYTEK device that converts and sends out the signal over mmWave. And then on the UE side, it gets really interesting because we have, again, both options. One is you could have a similar setup on the UE side where, we have a USRP and the server and TMYTEK and the whole system acts, but this time acts as a UE. So it has the UE software running versus the base station software earlier. But also you could replace that with a COTS UE device, must support FR2 and SA. And, we have some options and, you can reach out to us to understand what are kind of some of the current models that work. This kind of having the COTS UE connect to it kind of gives the whole setup a certain legitimacy, right? Like this is real, this actually works. And so this will provide like another really great starting point for showing different capabilities for mmWave. Then just kind of rearranging some of the same components, but in a different way to tackle another very interesting and key area. And that is for AI and ML. Once you're looking at implementing AI and ML models into your wireless system, you need to train them. And typically what you would do is you would start off with synthesizing some data with MATLAB or some of these other tools, and then use that to train your algorithm. We all know that real world many times is not what get in simulation. And I'd say for FR1, that was the case. And then for FR2, we understand even less. And so it becomes kind of what we've noticed is that it becomes, our models and so on for FR2 are not as good. And, there are many cases and different scenarios where, there are impairments and so on in the real world that don't get captured in this synthetic data. And performance of your model is going to depend a lot on how good the training data is, right? And how good the validation data is. And so we've created this reference architecture, and it's all free and open source, that runs on the USRP. And essentially what you're able to do is take this USRP out into the environment and collect real world environment data and store it in what we call as a SIG-MF format. It's an open source format. And this makes it easier for you to create kind of a data bank and then be able to train your model for different scenarios, right? And because the way we store the data, it has like not only the kind of raw RF data, but also like a header file that's able to capture a lot of the kind of scenarios or requirements or circumstances in which these data, in which the data was captured. And that kind of helps you to generate all these different scenarios. And then, so it works for FR1, and then for FR2, again, the same thing, we have the TMYTEK devices, and, you can start capturing data mmWave frequencies by plugging the TMYTEK up and down converters in front of the USRP. And all of this software to store and post-process the data and tag it correctly and so on, this is all free and open source, and it's available on GitHub. You can get the link from us, or it's there on the slide. And this whole thing was kind of partnered with Northeastern University and some top professors that are leading in this field. And they're using it to train their own models. And so we feel like we wanted to share that capability with others who are also looking to build AI and ML models and then train them. And then one other key trend that has again become like driving some fundamental changes in how we set up cellular communication systems, and that's ORAN. And so Open Radio Access Network, as most of you would be aware, this is basically a way to disaggregate the base station components and separate out the radio units and separate out the DU and CU functionality and the core network. And so vendors can mix and match. And what ORAN does is it standardizes the API. And so you can do this mixing and matching. And it also allows for a lot of very interesting research on optimization, on how can you use like rigs or intelligent controllers to intelligently maybe do networking level load management, all the way to, installing ML algorithms that kind of optimize things on the physical layer. And so from our side, like the X410 lends itself excellently to this kind of disaggregation. And so what we're working on right now is creating basically a ORAN compliant software that will run on the X410, and that will allow you to set up this 7.2 split network. And so, let's say you have an OAI stack, like an OAI server that runs the core network and the CU and the DU, and then we have a ORAN software or the ORU software that runs on the X410. And then, on the other side, you could have like a COTS UE or a USRP UE, and then you would have like an end-to-end ORAN compliant network. And what we would do then is obviously once kind of the first version comes out later this year, we would then add mmWave capability, right? And extend that same network to mmWave using the TMYTEK front ends and the BBox. I guess one thing also want to talk about, like when we talk about mmWave, especially in communications and 5G, the beam management becomes really key. And one of the areas that NI and TMYTEK have invested in is to make sure that like the beam management and the beam switching IP, they can get integrated. Right. And so you're able to switch beams on the TMYTEK BBox within like the timeframes required by 3GPP. And so that'll, as you set up like end-to-end 5G FR2 networks, this feature will become really important. So we talked a lot about mmWave. I also wanted to spend a couple of minutes on FR3. We mentioned it kind of in the beginning of my presentation, and maybe I just thought I'll share a little bit more. So 5G midband is something that got interesting, I'd say much more recently, maybe in the last year or two. And it's got interesting because of, I'd say a big reason was the challenges in deploying mmWave technology in real life, cost, and also kind of the difficulty in getting the mobility use case supported. Practical difficulties. And so midband seems like a good compromise, like it's still closer to sub-6 where we know how to deploy and where we're really good at it, and mmWave where we're seeing a lot of challenges, right? So midband seems okay, kind of an in-between. And so theoretically that should be kind of a good stepping stone, and it's not as crowded as the sub-6. So that's why this band has become interesting. Maybe like at the same time, there are definitely quite a lot of challenges before this can be kind of considered a real kind of a very concrete band for 5G or beyond 5G, maybe 6G, whatever you want to call it. And there are a lot of other applications or other, entities that use this band. And so we got to be careful on what's available. And then, there's some additional complications, like different countries have different areas of that band available, right? Versus for mmWave where nobody was using it. Well, not many people were using it anyway, right? Midband, almost everybody's using it, but not for communication. So we got to find some common bands that would work across a lot of geographies. And then there also has to be kind of a cost benefit analysis. Bandwidths available for midband are probably more than what's available at sub-6, but also still much less than what's available at mmWave and beyond. And so will we gain enough by deploying in this band? That's also not 100% clear, but definitely interesting to explore. So I wanted to maybe use just some of the things that we talked about today from a trends perspective, but also how kind of that fits into the overall picture, right? And so talked a lot about mmWave, FR3, and things like that. And what I want to share is that it's not like sub-6 is going away. That still seems to be, where the primary deployment is going to be. But could probably happen is there would be specific areas or specific circumstances or specific applications that would, which would be a subset of the overall huge communication basket, and where it will start to make sense to deploy these technologies for those specific areas. So maybe capacity could be one differentiator, places where it's very dense and has a very high data need that could absorb the cost required to deploy infrastructure at higher frequencies. Also, maybe specific applications like on-terrestrial networks, satellite communications, sensing, AR, all of these could also provide like specific use cases for the deployment of millimeter wave. So number of applications that could use millimeter wave have increased. And even though there were challenges for 5G, when you try to deploy millimeter wave for 5G, we still see this as kind of one of the most interesting areas, and we would like to support those looking to evaluate feasibility, looking to wait in this area. And that's why we have this partnership with TMYTEK and others, so that we can use the USRP platform and use some of this great software that's available to put it all together and provide you some great kind of starting point for systems, doing different types of applications. It could be end-to-end, it could be maybe sensing, more to do with a waveform, and also looking at AI and ML, things like that, right? So we have a pretty kind of strong lineup that could support a lot of these interesting research areas. And, we hope to be able to see you deploy some of this, and we would be happy to talk to you if you're looking to build some of these millimeter wave systems, and be happy to talk to you and share with you what we can do and how we can support you for that. Thank you again for joining us, for a chance to talk to you. And now hand it back to TMI Tech. Thank you.
Hello, everyone. Welcome to joining us today. I'm thrilled to have you with us as we dive into the exciting world of millimeter wave technology. I have an excellent platform developed by TMYTEK and NI for 5G, 6G, and future wireless systems, and I'd like to share it with you. We've got a packed agenda for you today, starting with the challenges in 5G and 6G wireless researches and how our innovative solutions are making a difference. We will walk you through the key features and the benefits of our solution, share the applications, and of course, we'll wrap up with the Q&A section. So please hold on your questions until then. Let's get started. Let's look into the challenges in millimeter wave and researches. The bandwidth of millimeter wave has always been a key reason why people want to utilize it. However, effectively using millimeter wave in communication is filled with numerous challenges. First up, signal attenuation. It's a fancy term for how signals tend to weaken as they pass through the air or obstacles, a particular pesky issue at millimeter wave frequencies, so that their issue of ranges and coverage. These high-frequency signals doesn't travel as far or penetrate materials as well as their low-frequency counterpart, all this limiting their reach. The second challenge we are facing is related to hardware difficulties. Designing those millimeter wave antenna, amplifiers, mixer, and so on is not only expensive but also complex. It requires specialized manufacturing process, which further drive up the cost. And let's not forget the alignment headaches. Keeping those narrow high-frequency beams on target is no small feat. Moving from challenges to obstacles, especially in research and application, we encounter more hurdles. One major obstacle is finding millimeter wave antenna array that are not just top-notch in quality, but also user-friendly. That's so easy. We are talking about a system that needed to be accurately calibrated and controlled via software. Is that easy? Never. Not quite. So the hardware intangibility is the first enemy to most research groups. And then there's a puzzle of integrating those antenna and RF front end seamlessly with software-defined radio, or SDR, to create a communication system that are both powerful and efficient. It's a tall order, but one we're committed to fulfilling. As you can imagine, one should take a good care of integrating the control interface and the data interface for millimeter wave devices and SDR. Additionally, we've carefully considered the link budget, and between devices. So many works to do. Fortunately, we have a solution for you. We have a solution to address the challenges and those obstacles just mentioned earlier. Let's check it out. Let's dive into the heart of the webinar today, our innovative solution designed to tackle the challenges we just discussed. We call the solution mmWave-SDR. So we proudly introduce our 28 and 39 GHz mmWave R front ends. These are not just any components. They include a user-friendly BBox, which is a beamformer, and the UD-box, which is a frequency converter. When we say integrated, we mean seamless combined with the NI USRP X410, creating a developed platform. That's not just as powerful, but also versatile across a wide range of applications. You can see that our work has extended the frequency range of SDR and provided capabilities related to beamforming. These changes have made a significant impact on the research community. Let's check in the key features of mmWave-SDR solution. One of our platform's most compelling benefits is its ability to turn ideas into reality at an unprecedented pace. Thanks to our complete hardware and software infrastructure, rapid prototyping isn't just a buzzword, it's a tangible reality. And this means shorter development cycles, quicker testing phase, and a faster iteration. It's totally a game changer for any project which is aiming to lead rather than follow. Next, let's talk about antenna arrays operating at 28 and 39 GHz. These aren't just any antenna. They come in configurations of 4x4 and 1x4, equipped with 6-bit phase shifter. This means precise, agile beam steering, crucial for overcoming those pesky mmWave challenges. Plus, with the support for the FR2 End-to-157 and End-to-160 band, these arrays are ready for the forefront of wireless communication standards. Moreover, beam control software is ready. It's ready for you, ready to go. You can control the beam using any engineering language you like, including LabView, Python, C, C++, and even MATLAB. Our focus on our performance is unwavering, as demonstrated by our UD-box adjustable IF range. Our UD-box supports 24 to 44 GHz bi-tunable local oscillator. As a result, the IF frequency ranges from 0.01 to 14 GHz. This feature ensures that our platform can cater to a wide variety of applications with a superior signal quality. And when we talk about exceptional EVM characteristics, we are promising that your data integrity remains intact, no matter how complex the project you are. And just like a BBox, we believe the innovation should be accessible. So that's why we also developed the API for UD-box to speak in your language, whether you're using MATLAB, Python, and many so on. Our API ensures that controlling of the local frequencies is as easy as writing a new line of code, a few lines of code. Along with the Beamforming API, this is for broader audience, enabling researchers and the developers to focus on innovation rather than wrestling with complex control mechanisms. No more complex control. The most crucial point to highlight is our seamless integration with the NI USRP, which includes several key features. We have SPR hardware control for fast beam swapping mode. ATR stands for Auto TR, that enable TDD for 5G FR2 numerology. And of course, UHD for BBox and UD-box control. Additionally, the NI LabView bundle provides a great start point for users. This system is truly flexible because of what's been done. Enables data path using standard RF cables, and the control path use standard PC-equipped interfaces. This makes the application simple to put together the building block of Legos, so you can use our devices and the USRP to combine any kind of solutions for different topics such as MIMO, and if you want to do ORAN, this is possible. If your research is for JCRS or ISAC, which stands for Integrated Sensing and Communication, the setting up is straightforward. Now let's look into the possible use cases for what is research. One of the projects that I work with US and CSU is that we leverage the power of beamforming and the beam control API and integrate it seamlessly with NI SDR. We managed to accelerate the performance of a channel sounder. We speed it up about 50 times faster than the system utilizing Jimbo technology. And this significant leap sets a new benchmark in the field. Our approach has opened up new opportunities and efficiencies, proving that with the right technology and a dedicated team, we can push the boundary of what's possible. In another recent breakthrough, our team has successfully demonstrated a mmWave transmission over a distance of 100 meters in an outdoor environment. This achievement marks a significant milestone in mmWave-SDR system and open up more research opportunities. Imagine you have a system you are able to transmit mmWave frequency ranges for such a long distance in a tested platform. So this is close to what the real world needs. On top of mmWave-SDR, I'm extremely honored to announce to all of you that our mmWave-SDR system can be effortlessly upgraded to a complete end-to-end 5G FR2 platform, as illustrated in the diagram, by connecting the OAI box platform, which is developed by our partner OBSmart. Our solution instantly transformed into a 3GPP-based platform capable of end-to-end transmission between G-Node B and the UE. This advancement marks a significant leap forward in our capabilities, enabling us to meet the growing demand for high-speed, reliable 5G communications. This is also a great platform for the researchers like you. We build the tools, you use the tool, you create your magic. Let's take it a step further. I'm thrilled to share that NI, in collaboration with us, offering a split 7.2 ORAN reference architecture based on the mmWave-OAI box framework. This innovative move will provide a reference platform for ORU, ODU, and OCU. This development is not just a testament to our commitment to advancing 5G technologies, but also it's a clear indication of our dedication to open and interoperable networks. By doing so, we are paving the way for more flexible, efficient, and scalable network solutions. Setting a new standard in the industry, of course. The system we're going to offer here is very unique and it's open. So we believe this will bring you the great values in your research. You can change anything, you can touch any protocol layers and test the performance on top of it. At this moment, the solution based on OAI box now support both the split 8 and with the commercial ORU based FR1 split 7.2. Even more impressively, we have successfully achieved communication with iPhone 14 Pro Max. This milestone not only demonstrates our platform's versatility and cutting-edge capability, but also marks a significant achievement in enhancing connectivity for the latest consumer devices. Let's check the video a little bit. by our partner OBSmart to demonstrate VM and commercial ORU connected with the OAI-based CU and DU. The system communicated with the FR1 iPhone successfully with a certain tool. All right, so from the video, you can see the readiness of a couple. Right. And next, imagine when we step into the future, when your phone doesn't just connect you to the internet, but also sense the world around you. That's the magic of 6G with JCRS or ISAC. It's likely giving our device superpowers to communicate and perceive their surroundings all at once. This isn't just about a faster download, it's a game changer for everything, from self-driving cars, making them smarter, safer, and transformation our cities with real-time and advanced monitoring. With the 6G, we're not just connected, we are intertwined with the digital and the physical world like never before. Sounds good, right? Again, when your research steps into new era, you also need something like mmWave-SDR. It's capable of all of this. So you can edit your waveform, integrate your sensing and communication algorithm all in one devices, and you can explore mmWave capabilities together with your modem and so on. So you need mmWave-SDR. Now in 6G, people are even talking about non-terrestrial networks. NTN essentially is a communication network that goes beyond Earth services, reaching into the air, space, and sea. This network uses components like a satellite, high-altitude platform, and aerial vehicles to ensure global connectivity is seamless. All right, we need a platform like mmWave-SDR for the research and the development. For most of satellite communication or even high-altitude system, people tend to use KU or the Ka band. In terrestrial network, for mmWave, people are using 28 and 39 GHz. No matter you from the approach from NTN or from satellite and back to the ground communication, you will need a platform which is capable of dealing with a DSP and mmWave. So that's how mmWave-SDR can provide you the value. And of course, integrating AI into ORAN's radio intelligence controller or RIC presents a unique challenge. Definitely AI and machine learning is the great power can enhance the communication systems. The challenges of integrating RIC, including high-quality data availability, interoperability, and the standardization issue. Of course, resource constraint and so on, there's a significant hurdle. Lastly, integrating AI raises security and privacy concerns. To tackle this, robust security protocols and regular audits are essential to protect the sensitivity data and ensure network integrity. Overcoming these challenges, we'll need a flexible and versatile platform to explore the potential solutions. So again, we believe SDR plus mmWave capability can provide you everything you need for next generation researches, no matter it's in sensing or communication or the fusion of these two. So thank you for watching the webinar today. I'm so happy to have your participation. Now, please raise your questions. We will try our best to answer you. Thank you.
Hello, this is Ethan from TMI Tech. It's my pleasure to introduce the latest result. TMI Tech and OBSmart work together. We enable FR2 on OAI. So here you see a true FR2 OAI transmitting both the uplink and downlink were transmit in mmWave band, 26.5 GHz we have a G node B, we have a UE. As you can see, USRP X410 along with our BBox and UD-box as a RF phone in. OI box, as usual, we have a core network, the CU and DU. Now here, I launch UE code. The stack is running, and from here, you're able to see the testing result, which is 60 megabit per second throughput, can be seen from OB Smart dashboard. So that's where we are. Next, we are working on TDD. We will enable big switch and the TR switch on BBox along with the USRP. So after this, you will see one BBox for G node B, another BBox for UE. And then we're done here. It is a very important milestone for next. Thank you.